Thanks, Bruce, and thanks for inviting me to your beautiful institute here. It's just an inspirational facility. And I hope that my talk can give you some things at least to think about and some awareness of what's going on the topic of engineering minors. Okay, so what are we going to hopefully get out of this? Some idea of what engineering minors are, what's the need for engineering minors, what might be some opportunities for engineering programs to offer minors, what's some of the work that's been done, and a little bit of data that we have on some of the perceptions and interests of students, non-engineering students in engineering minors. I want to mention support for this work is from the National Science Foundation under a CCLI grant, and this is being done in collaboration with Hope College, Iowa State, Ohio State, and Rice University. And the goals of our research are to develop a minor that's feasible, common, useful, to investigate the structure, determine student perspectives, also find out a little bit about employer needs, and try to find ways to promote the idea of an engineering minor more broadly within the engineering community. Okay, first, before we dive into this too much, we should just get on the same page about what we mean by a minor or a certificate. So the idea is typically this would be 20 to 28 credits, maybe 5 to 6 courses, depending on how your academic year is broken up, or the equivalent. Most courses being in the same department, include courses beyond the introductory level, and an intent of both breadth and depth in a subject. But of course, not as much as a full major. So, why do we need engineering minors? What's the value here? Well, a few things. First, preaching to the choir here, so to speak, but we live in a human-built environment. If you look around this room right now, the only two things in here that are not made by humans are our bodies and the air we're breathing. Everything else has been the product of the engineering process in one form or another. Most problems today have a technological component. The interaction between technology and society is complex, and technology is always evolving. So the pervasiveness of technology is certainly an important aspect. Now, towards this recognition, in 2002, the National Academy of Engineering published Technologically Speaking, Why All Americans Need to Know More About Technology. And in Technically Speaking, the NAE pointed out this paradox that we live surrounded by a very complex technological environment we've created for ourselves, and virtually no one has a strong understanding of how that works, or to be able to think critically about that technology. And more recently, in improving messages for improving public understanding of engineering, the NAA has pointed out that to be a capable, confident citizen today, everyone must know something about engineering, or should. Also, it's an important priority of employers of our college graduates. The AAUP, Association of Colleges and Universities, did a survey of employers, and their highest priority, 82% said they would like graduates to have more knowledge in the area of concepts and new developments in science and technology. So this was their highest rating, which was actually higher than, for example, the ability to work with numbers and understand statistics. That was rated 60%. Understanding technology is 82%. So clearly the employers of college graduates seeing this as an important outcome of undergraduate education. Non-engineers themselves are interested in understanding about technology. Some various surveys that have been done, and what non-engineers are telling us is that they have an interest in familiar technological devices. They appreciate hands-on experiences. They want to develop a sense of empowerment with technology as opposed to being powerless, and develop a sense of demystification about the technological environment that we all inhabit. So what are some of the challenges given these needs? Well, one of the challenges is that if you look at the undergraduate education, most colleges or universities have some sort of a science requirement. And how do most non-engineering students, non-STEM students, satisfy that requirement? Well, they take a science course. So kind of pushing the envelope here, and hopefully I think a friendly crowd, but if you think about a non-engineering student taking a class like Astronomy 101, Not that that's not valuable, but to what extent is that going to help them to be an informed citizen, a capable consumer in these areas, things like renewable energy, industrial innovation, computer security. These things are important, but it's stretching it to think that that's going to provide the background that's really empowering in these areas. So that's one extreme. So what's the other extreme? Well, okay, everyone should be a double major, engineering and something else. All right, let's do the numbers here. Well, the something else, first, is, again, depends on how your academic year is broken up, but 36 credits, the equivalent of 9 semester-long courses, is the something else. What about engineering? Well, an ABET accredited degree is 48 credits, so that's 12 courses. Requires 32 credits of math and science prerequisites, that's 8 courses, semester-long courses. These are highly sequenced. They have to be taken in appropriate order. There's a large number of them. So you add them all up, we've got 20 courses. So 20 and 9 is 29 courses. A typical degree program is the equivalent of 32 courses. This only leaves 3 courses left for everything else the students need to do in college. So for most students, engineering plus something else is not really a practical option to developing an understanding of our technological environment. Not that some students won't be able to do it, but for large numbers, not going to be practical. Okay, so that's strike 1, this is strike 2, now we're up to strike 3. There's very little in the way of engineering service courses. So what we mean here is that courses offered by engineering departments with a large population, maybe even a majority population of non-engineering students who are not planning on pursuing professional training in that area, but are taking the course as part of their general education. So these are things like Econ 101, Psych 101, and Physics for Poets. By and large, engineering courses are taken by engineering students. So classic there, circuit analysis. Don't see many non-engineers in circuit analysis, solid mechanics, thermodynamics. So, and part of it is our self-image of engineering. Our habit is to focus on students who can recreate the hardware that existed 10 years ago, and that's what we do. Now, to be fair, the other side of the coin is that in many colleges and universities, engineering programs are excluded from participation in the general education program, either by politics, prejudice, or pressures, or habit, in the sense that engineering oftentimes is classified as a professional school or a pre-professional program, and the courses that satisfy the core curriculum or the general education requirements are usually from the College of Arts and Sciences, which does not include engineering. So in many places, even if engineering wanted to offer a service course, they would not be allowed to, or would find it very difficult to be able to get accepted into the core curriculum. So this is kind of strike 3. So if we look here, so some of the structural barriers for a non-engineer to understand about technology. On one extreme, the one science course. On the other extreme, the impracticality of double majoring. In the middle, a non-existence of engineering service courses. So this leads to very limited opportunities for non-engineers to understand, develop an understanding of engineering and technology. Okay, so this is kind of the problem. But what are some new developments that are hopefully supporting the idea of developing engineering minors or certificates? Okay, first, student interest in minors, double majors is increasing. Some of the data that's available is that there's over 5 years, from 1998 to 2003, there was a 50% increase in the number of students graduating with double majors, so that 1 out of every 4 students had a double major. Now, there's no official data for the number of minors, but I think anecdotally we could notice that a lot of students are interested in majoring and minoring in something. So the official sort of available data is supporting that in terms of more students double majoring for a variety of reasons. Another development in favor of, or pushing towards the idea of broadening engineering education is if you're looking at, this is from Science and Engineering Indicators 2010. Back in 1970, what we'll say then, this is a normalized population of students. So about 20 out of every 100 undergraduates was pursuing a degree in engineering or science. out of about a little bit more than 40 total. So back then, about 1 out of every 2 students was an engineering or science student at a typical university, about half. What about now? Well, now there's about the same number of us, but a lot more of them. So engineering enrollments actually haven't gone down, but they've become smaller in proportion to the overall campus population. So this is creating pressures on engineering's share of the overall allocation of campus resources. Now, in 2007, the National Science Board, which is the governing board of the NSF, so this is the board that sets the policy of the NSF, provides top-level advice to the President and Congress. In their study called Moving Forward to Improve Engineering Education, they had 7 recommendations for engineering education. One of those 7 was that engineering departments should consider offering courses in engineering to non-engineers. So this is about as high a level of policy support as possible for this idea. Okay, back in the trenches, we see that some schools, for various reasons, have been able to offer very successful what would be called service courses to a primarily non-engineering population. One example is David Billington at Princeton. He's taught for more than 2 decades a course called Engineering in the Modern World, which focuses on the political, ethical, scientific, aesthetic aspects of the 200-year evolution of engineering, with kind of an emphasis on infrastructure, David being a civil engineer, kind of favoring transportation, large structures, bridges. And this course satisfies the non-science major science requirement at Princeton, or one aspect of it. So this is one course. Another example of a department that was able to offer a wide variety of courses in a more expanded program was at Union College. Oops. They offered, developed what they called their converging technologies, which looked at technologies that were at the overlap of the sciences and engineering in other areas. And they were offered 30 new courses taken by non-engineers and engineers over a 5-year period. It became something that Union considered one of their pillars of excellence, that they put in all their admissions type of materials. So we have some evidence that some places managed to figure out ways to do that. One other thing is that engineering has been able to get a foothold in the general education core in a couple different ways. So on the left here, schools like Bucknell, Princeton, Dartmouth, University of Illinois have the words understanding engineering and technology as part of their university core curriculum goals. Oftentimes this is the efforts of faculty members over long periods of time, gradually affecting change, but nonetheless it happened and provides important precedent for the rest of us. On the other side, at Yale and University of Virginia, courses taught by engineers satisfy the science requirement for their overall distribution. So there's been some important example setting success stories here. So this might actually be a market niche for engineering. There's an increasing student interest in minors. Decreasing relative engineering enrollments might produce some pressures to contribute more broadly to the university environment. Some existence of several successful courses, openings in the core curriculum, and students seeing a certificate as a desirable credential to have in their future careers. Okay, so now I say, fine, this looks like a good idea. A few positive developments. Is it possible? Is it practical? Can it be made flexible? So let's look at 3 different aspects of this question. So first, the possibility problem. Now to investigate this, we're going to need to stop for a minute and just get on the same page in terms of what we mean by developing a broad understanding of technology. So in technically speaking, the NAE stated that technological literacy, or the broader understanding of technology, is more than just the ability to work with specific pieces of technology. So what we're saying here is this is more than just what might be considered the traditional realm of engineering, is the hardware, the specifics of the hardware, but a broader consideration of all the aspects that go into creating, developing, using, modifying, directing technology. Now, not to create kind of a civil war within engineering, but this is certainly the intent of things like the Engineer of 2020, which is trying to broaden our self-image in terms of what we see as our important things to take into consideration as engineers. So with this broad definition of technological literacy, a workshop was convened at the NAE in 2007 that said, okay, suppose we want to do this. Is it possible? I mean, can we even think about engineering departments offering courses to non-engineers for the goal of establishing a sense or an understanding of technological literacy? So this particular workshop, there were 35 participants. They looked at, basically tried to collect up all the examples of successful service courses for engineers that had come into existence at various places for various reasons. So these were offered by engineering departments for non-engineering majors and had no prerequisites. Okay, so what did the group find? Well, we found that we needed to agree first on a definition of what was meant by technological literacy and kind of a working level. So a parallel effort that was going on at the same time was the ITEA, the International Technology Education Association. Now this was basically the evolution of what back in the old days used to be vocational education, but had moved towards a broader definition and was trying to influence the K-12 curriculum to include technological topics. Now, the NSF and NASA funded a very large study, involved hundreds of people, lots of professionals in all sorts of technical areas kind of weighed in. And they came up with 5 areas defining technology, and within these areas, 20 subtopics that should be considered to have a broad understanding of technology. So this particular workshop agreed to use this definition, even though it was originally intended for K-12, just as a working definition of technological literacy so that we didn't have to spend the entire workshop debating over what should be included. So this was good enough. So interesting result. If we looked at all the materials covered by all the courses plotted against the standards, we found that, so what's on the left here is the fraction of courses from this aggregate group of 22 courses were eventually studied that included some level, sort of meaningful level of addressing that particular content. So like a 0.79 here means that 79% of all courses included something about the characteristics of technology and so on. That except for the area of agricultural and biotechnology, in this collection of material from 22 courses, there was enough stuff to cover all those standards with existing courses that had been taught by various engineering faculty. So what this means is, the answer is yes. It's possible. Engineering faculty have been creating technologically literate in some fraction of students, but what it means is that the engineering minor is 22 courses. So you have to take all these courses to get all these pieces. But I think the important thing is it's established that engineering faculty were doing it in a very dispersed little pieces here and there, but it's been being done, so it can be done. So the next aspect, which was of the workshop, was to say, is there a more feasible way to do this than 22 courses? Okay. So the next thing was to look through all these courses and say, is there some way we can find some standard models, some subset that forms a sort of a basis vectors to span the solution space of technological literacy? Now, what was interesting is that if you took these courses that were represented, they seem to be classified into 4 types. And these are the 4 types. Some of them were what we could be considered survey courses. So these cover a wide range of topics, sort of big picture courses. Some of the courses were focus courses, looking at more narrowly defined topics within technology. Some were focusing on creation or design. And then another group was courses addressing critiquing, assessing, reflecting, connecting, engineering in context, technology, and society type courses. So just to give you a little bit more specific examples here, here's some survey courses. So these are courses taught by engineers out of engineering departments for a primarily non-engineering student body. So a course offered by Dave Ollis called How Things Work at North Carolina State University covering the principles of operation of a wide variety of topics, cell phones, guitars, photocopiers, digital camera, sort of a broad spectrum of technology, a survey course. Another example of this type of course, not exactly the same, is Bill Hammack at the University of Illinois has a course called The Hidden World of Engineering, where he looks at common objects like the pop can and describes the engineering. Students study the engineering of these common objects. And Bill's point of view is that these common objects that we take for granted are masterpieces of engineering. In fact, the simpler, the more of a masterpiece that it is. But again, covering a wide range of topics, intending to be a survey course. So these were the survey type courses. Some examples of focus courses. A course taught by Camille George at University of St. Thomas, which is not in the warm part of the country, but in Minnesota, where I guess it's even colder than here. But her course on fuel cells was for non-engineers. Talks about, it was a hands-on design, lab-oriented course with aspects of safety, economics, policy, the hydrogen economy, open to anybody in the college with no prerequisites. Another example, a course taught by Grant Norton and David Barr, actually developed by them with NSF support at Washington State University on materials, the foundations of society. Taken by non-engineers, satisfies part of the Washington State core curriculum. Points out the importance of materials in human development and also some of the engineering and science aspects of different materials. So these would be sort of the focus courses. Design courses, a couple examples here. Courses primarily for a non-engineering population. A course taught by James Bache at Bucknell called Designing People. This was a freshman experience course for anyone in focusing on the engineering design process. Rice University teaches Introduction to Engineering, open to the entire college, university. Engineers, non-engineers take the course and they collaborate on projects. The sort of central theme of this course taught by James Young is robotics, building robots. Okay, finally the fourth category, the Connect, Assess, Reflect category. An example here is a course taught by Bradley Bishop at the Naval Academy called Emerging Technologies, where they look at new and emerging technologies from a global perspective. What's the impact going to be? What are the factors that affect technological change? This course became the most popular course at the Naval Academy. It's a required course for their honors program. And as Brad tells it, God's honest truth, men in dark suits would come, ask a couple student volunteers to go to a room, describe to them a certain thing that they would like them to think about, and got their feedback. They found that the students had, as you might expect, certain insight into how certain technologies might affect the broader context. So this is the idea of a Technology Connect type course. Another course in this category, very different focus, is looking kind of backward, a course taught by William Lohrendorf at Eastern Washington University, where it's looking at the impact and consequences of past technologies, a lab course where they actually recreate, make, use technologies of the past, stone tools, recreated Japanese armor. So it's an example of the fourth category of courses. So all the courses that existed seemed like they could be roughly sorted into those four categories. Okay, now a really important, we found, aspect here is that these four areas of courses actually seem to be fairly consistent with what the National Academy's Committee on Assessing Technological Literacy saw as the four major content areas of technology that should be considered. These two groups working independently of each other, no communication. Most of the courses developed by faculty working in isolation, just pursuing a good idea. It seemed like they overlaid very nicely on the four categories of technology and society. Those are the assess courses, design, obviously design courses, products and systems, the focus type courses, and then sort of the core concepts were the survey courses. So these course models kind of self-organized into a way that was consistent with what the NAE committee thought would be appropriate categories. Now, one final thing is that if you actually look at some of the other areas of study in the university, roughly speaking, they have a similar structure. So say English or music, well, you have your introductory courses, English 101, Music 101. There's focus courses like British literature or jazz styles and analysis in music. There's the create, apply type courses. In engineering, it's design. English, it's writing of various types. Music might be interpreted as composition or performance. And then each field has its connecting itself to a broader context type of courses. So history of music theory, literature and cultural difference in English. So this leads to the idea that an engineering minor now or certificate, which might be have the intent of developing a broad understanding of technology, sort of an empowerment of the non-engineer, might have 5 courses, maybe organized this way: a survey course, 2 focus type courses, a course focusing on design, and then an assess or reflect type course. I should mention that the assess, reflect, connect course clearly falls under the realm of the science, technology, and society programs that exist. But this particular research project was looking at just classes taught by engineering departments. So there would definitely be some natural overlap with STS type programs in this area. So some things to support this type of structure. Well, it's consistent with the National Academy of Engineering's definition of what constitutes technological literacy. That's a good sign. It's consistent with the structure of other disciplines in terms of how to bring someone into developing understanding of this area. And what I find actually most compelling is it's consistent with how people doing this self-organized anyway. Okay. Now the last, so this is, it's possible and it can be made practical. Now is there a way to do this a little bit more flexibly? So take this to the next step. So rather than defining an engineering minor as successfully sitting through some number of classes of a certain title, actually specify what the learning outcomes should be. So in completing a minor, what should a non-engineering student be able to know and do? And state these in a measurable term. So this is following in the spirit of what ABET has done for engineering, saying we're not going to recommend a set of courses, we're going to recommend a set of outcomes that you must establish that your program achieves in your students. And also, even broader than that, if you look at the AACU, is suggesting that all areas move towards a sort of outcomes-based definition of the goals of education. So this is the last phase of our current work. It's to develop some objectives and then some measurable outcomes. So in terms of objectives, let me just pause for a second. I want to give a little handout. Well, if someone is technologically literate, that will sort of fall under 4 objectives. And this is a template that's provided by AACU. I always get them confused with AAUP. That have certain knowledge of the technological nature of the physical and natural world, have the ability to meaningfully engage big questions of a technological nature, have characteristics of personal responsibility with respect to technology, and have the ability to synthesize and advance technology across a range of domains. So within these 4 areas, then, we would see, now hopefully this answers your question, specific measurable outcomes that in completing a series of courses, just like in the case of ABET for engineering, students would demonstrate. So I'm just going to highlight a few of these, and in the handout they're all listed in detail. But for example, they would be able to define basic engineering concepts. So this is sort of a knowledge level type of capability. Things like what's meant by a system. If you talk about having a meaningful dialogue on a national policy issue, there needs to be a general understanding of what we mean by a system or constraints. In the ability to engage category, that a student who's technologically empowered would be able to describe the development of use of technology, would be able to evaluate trade-offs, would be able to balance costs and benefits, both economic and social. So this is a measurable outcome that some students may bring in from other experiences. In the area of responsibilities, would demonstrate an ability to be self-educating about technological issues. And in capabilities, say, for example, be able to think critically and creatively regarding technological issues. So thinking critically and creatively was sort of the compromised language that would include being able to do design and some type of calculation, some kind of analysis, but stated a little bit more broadly in terms of thinking critically and creatively. Okay, so the idea here would be that just like the ABET A through K, programs would be at liberty to, number one, accept these outcomes and then decide how to meet them based on what works best for your particular program. So, all right, so some examples which we'll look at how this has been implemented in some specific schools. So one example is Iowa State has a minor in engineering studies. The point you bring up is a good one. Actually, even what to call these is oftentimes the most contentious issue. Theirs is 32 credits, 30 students in the program. Theirs is a combination of existing engineering courses. They have an interesting idea with separate assignments for non-engineers. So they use existing engineering courses with two tracks. Minors only courses, and the director of this program will not allow any regular engineering faculty to teach them because it scares the students away. They're much more successful when taught by graduate students. And they've had an example, at least one, of a student pursuing an engineering minor, deciding to go on to graduate school for a master's degree in engineering based on her experiences. This is just a clip from their website. And they have a very kind of engaging series of like short clips that run to help students see how an engineering minor might connect to something that they see as important. This was an initiative of the engineering school, so it came from the engineering school back out to the university. They weren't able to get into the core, but they were able to offer this minor as a credential that was attractive enough to bring in students. And also, Mani Mina, who teaches this, is very engaging, very student-friendly type of instructor. So they put this out as something that would bring in students and stand on its own. So they're not getting, say, core curriculum credit. And to that point, every school has its own little unique sets of circumstances. Another example, kind of the other extreme, is Ohio State. They have two minors. One they call engineering minor in sciences, which is a calculus prerequisite, and a technological studies minor with no prerequisite. Recently approved. They've got 3 students in each, 2 new courses, and then the rest were existing courses. But in the case of Ohio State, this was a top-down initiative. So this was the highest level of the university saying, doing a core curriculum revision, saying we need to do something about technology, actually going to the engineering department program and saying, what can you do here? Interestingly enough, huge debate about using the word engineering in anything. So the compromise was engineering minor in sciences. Rice, they've just established their minor. They have this very strong gateway course. A couple of interesting ideas. Their minor is going to be set up, or is set up in a way that meets certification for K-12 engineering teaching. A lot of, in the K-12 sector, lots happening. And of course, the question is, if we're going to have engineering in K-12, who's going to teach it? Teachers have to be trained. So Rice is seeing that their minor is going to provide certification to teach K-12 in the Texas system. Also, in reference to your point, it's outcomes-based. So students can establish they have competence through non-course relevant experiences like internships, extracurricular activities, participating in things like Engineers Without Borders, as a way of making the program more flexible, more student-friendly. But a key point is that programs are trying to meet their individual circumstances, be a little bit creative about meeting the students halfway. Now, one other interesting example here is Olin College. Olin is a small engineering-oriented school. They have an interesting collaboration with Babson and Wellesley. Babson has a sort of a business emphasis. Wellesley, an all-women's liberal arts college. Their campuses are in close proximity. In fact, Olin and Babson campuses adjoin each other. They're offering an engineering certificate based entirely on regular Olin engineering classes. Now, they have 16 students in the program. 6 of them are Wellesley students. All of them are science majors, thinking about going to graduate school, wanting to get a little bit of taste of engineering, maybe something to improve their chances of getting accepted to the school of their choice. From the Babson students, the Olin certificate satisfies part of the Babson Entrepreneurial Technology Program. So again, it's sort of a localized kind of situation that works well for these 3 schools. Then I think the last thing we need to look at is a lot of schools have the engineering light minor, which is typically maybe 20 credits. And you pick sort of the subset of courses like intro, solid mechanics, circuit analysis, thermodynamics, add up to 20 credits, call it an engineering minor. So does this meet our definition of technological literacy? Probably not quite. Certainly would probably most likely be very good in the design and focus areas, but in terms of having these students be broadly empowered, need something possibly in sort of the survey course to give a big picture and something of the connections to give engineering tied to a broader context. Okay, wrapping up in the last couple slides here, some results from surveying students in connection with our support from the NSF. So some focus groups were done with students enrolled in these programs in Iowa State and Ohio State. And they have some interesting comments like, get the word out. A lot of students would consider it if they knew about it. Another different student, hey, it's a marketing problem. A perception that you have to take a bunch of math. So clearly this quantitative issue, it's the elephant in the room, and it's got to figure out some way to work around it. In addition to some practical things, like make the administration signing up easier. A lot of signatures you need. The word engineering scares students, soften up the advertising. What the students are telling us is they're seeing value here, but it's not going to be a build it and they'll come kind of thing. There's going to have to be some savvy presentation of this to the broader campus community. Last bit of data here is from a course that I developed and teach at Hope College. It's a survey course called Science and Technology of Everyday Life. It satisfies the lab science requirement, focusing on a lot of hands-on laboratories, sort of developing the sense of empowerment, picking some main topics like automobiles, electronics, and computers. Some important data here. This is from an instrument called the Motivated Strategies for Learning Questionnaire, the MSLQ. So pre and post data are showing that students going through this course are showing an increase in intrinsic motivation, that's genuine interest in the subject, an increase in self-efficacy, that's self-confidence in the subject, a decrease in test anxiety in this area, an increase in task value, and an important positive control here is that extrinsic motivation was unchanged. In other words, that's motivation for reward. I'm doing this for some kind of reward that I'm going to get out of it. So this particular course is moving student attitudes in all the right directions, in addition to showing separately content knowledge increases. Now, when this group of, in this case it was 91 students were surveyed, in their potential interest in engineering minor, 40% said it would be useful and the topics would be of interest. 15% said they'd potentially be interested in pursuing an engineering minor, and maybe about 7 or 8% said it would actually fit into their schedules. So what we can take away from this is that for a workable engineering minor, you need the strong gateway course that hopefully can fulfill some portion of general education requirement. Students have a positive experience, they learn something, it draws them in. Interestingly enough, this is very consistent with what I think a good basis of comparison is Econ 101. So about 5% of all the students who take Econ 101 nationwide end up as economics majors. It's a course that most students haven't had in high school. So they go into it, they have a good experience, they get intrigued with the subject, they pursue it to a major. Now in engineering, it would be the minor. They would stay in the program long enough to complete the minor. So our conclusions. There certainly is a need for non-engineers to understand technology. Minors and certificates are becoming an attractive option. There's a potential for flexibility. There's some interesting specific implementations like dual track engineering courses with both types of students enrolled. The interesting idea that, we might possibly be able to increase our pool of engineering graduate students through this route. Some interesting possibilities being able to offer certification for K-12 teachers through engineering minors. But there are some challenges. We definitely have to craft the minor in a way that is attractive to non-engineers. In particular, it seems like getting a sense that some very strong courses to draw students in who aren't necessarily predisposed. So finally, I just would like to acknowledge support from NSF again, and also CASEE and these collaborators. So thank you for your interest, and hopefully I have a little time for questions.